Yeah. Yes, so first of all, I would like to thank Etera and Pietro and the organizers of this school. It's my great pleasure to talk in this summer school, and also an honor to be the first speaker. So as Etera mentioned, this school is supposed to be focused on loop quantum gravity, but I have chosen to present a topic which is actually slightly unrelated, although my goal is to convince you towards the end of the lecture that this is useful and this contains useful tools for quantum gravity. So the topic is on symmetries and charges in general relativity and gauge theories. So I just would like to start with a few remarks. So the first remark was, as I just said, thanking the organizers. I also want to thank the audience for joining this talk. The second remark is that, so this topic, which I will try to cover, is based, of course, on the work of many, many people, and both really old work and more recent work. And I apologize in advance for not probably properly citing all the relevant references and all the relevant people. The other remark is that this topic is very vast and contains many different directions and ramifications. So I have chosen a particular path, which is just a personal choice. And I hope that, that this will contain enough useful information on this very broad topic. And so unfortunately, since this is not a physical school where we can interact on the blackboard, and it's also the first time that I give a long lecture using slides on Zoom, I'm trying to be as detailed as possible and flashing everything point by point. So I just encourage you to write things down and try to keep track of all the details and maybe work out the examples for yourself. And as Etera said, and Pietro, we will only take a few selected questions during the lecture and make time for more questions at the end. So this is the outline of the talk. So this talk is supposed to cover 5 hours. So first I will give an introduction, then introduce some technical tools called the covariant phase space formalism. And then we will try to apply this formalism and to extract information from 3-dimensional gravity and then 4-dimensional gravity. Then probably tomorrow I will discuss what I just chose to call advanced topics. And if I stick to this schedule, on next Monday, what I would like to do is present some numerical calculations and present a code that I can share with you that enables you to kind of compute explicitly things which we have seen during these lectures. And also the goal is that this is an introductory set of lectures to more advanced talks, and 2 of them in particular. One is next week by Andrew Strominger, and this is on the infrared triangle in quantum gravity, because as you will hopefully see, discussing this structure of gauge theories has important applications, especially in recent years, when studying infrared properties of gauge theories. And also there will be a talk by Laurent Friedel at the end of next week, I think, or maybe in 2 weeks, on a notion of local holography. So hopefully by the end of these 5 hours of lectures, you will be able to appreciate and understand these more advanced lectures. So let me start with the introduction. So our basic motivations and goals for this lecture are to understand gauge theories, for example, familiar Yang-Mills theory or gravity, in bounded regions of space-time. And I put bounded between quotations here because in fact, we will consider boundaries which can actually be located at infinity of your space-time. What I would like to explain and discuss is that when we consider...
Marc, yes? Sorry, I want just to say to everybody, I think that I unlocked the CAP. So if you know someone that was not able to connect, please invite him to do it again. And now we should have for real 500 people CAP.
Okay, thanks Pietro for fixing this. Yeah, so the important thing which we have to discover and understand together is that when we consider gauge theories and in the presence of bounded regions, there are certain extra features which can appear on these boundaries. And in particular, we will talk about the notion of charges and also algebras of charges and even maybe degrees of freedom. So this is the goal, is to unravel all these structures which live and appear on boundaries. So the reason to do so is twofold. So first of all, at the classical level, you will see hopefully that this enables us and helps us understand the structure of the classical theory, namely the structure of the field equations and the solutions of the field equations of the theory. So this in itself is already something very desirable. And this was the motivation for most of this work, especially in the gravitational context, starting in the 60s when people were studying gravitational radiation. And then a more recent topic is, of course, once we understand properly the structure of the classical theory, this can also tell us, in a sense, lay the foundations to build the quantum theory. And what we hope, and what is also coming out of lots of interesting recent work, is that understanding this classical structure of gauge theories, especially gravity, when we have boundaries, this can lead to very new and very useful insights. For example, as you may already know, the notion of holography is an insight which came from thinking about gravity in bounded regions. So the roadmap to understand the plan is quite simple. I want to start on very common ground so that we can all understand what is happening. So to do this, we will start with usual Lagrangian and Hamiltonian formulation of mechanics and discuss the notion of symmetries and Noether's theorem. Then what we'll try to do is try to generalize these structures to gauge field theories and work out all the subtleties which are involved when we go from simple mechanical systems to field theories, and in particular to gauge field theories. So field theories with gauge symmetries and gauge freedom. And then once we understand what the subtleties, and once we have the technical tools to discuss gauge field theories, we will study a short glimpse of what this can tell us interesting about 3-dimensional and 4-dimensional gravity, and also hopefully about quantum gravity. And yeah, just as a comment, because I see the question in the chat, I will provide, of course, I'm happy to share the slides so you can have all the material for yourself. So to continue with the introduction, I want to start with something which is a cornerstone of modern physics, which is a very powerful theorem by Emmy Noether. And so this theorem, we can think of it in the following way. So first, I want to make two basic statements, which we should be familiar with, and then derive the theorem from these two statements. The first statement is that on the one hand, if you consider, let's say, a simple mechanical system with position variable q and time t, we know that the on-shell variation of the action of the theory is a boundary term. So here I have written this schematically, I have written the variation of the action. From now on in all of the talk, this wiggly equality will mean on shell. So once the equations of motion hold. And this is just a statement that on shell, the variation of the action is just a boundary term. And you see that this boundary term here, I have rewritten here in the second equality in terms of dl by dq dot, which is just a momentum p conjugated to the position q. So this is our first observation. The second observation is that if we now consider a variation delta, which is a particular kind of variation, namely a symmetry, which is why I denote this variation by delta epsilon. So the statement is that such a variation delta epsilon of, say, the position q is a symmetry if for all q's of t, there exists some quantity, which I just, for convenience, choose to call b. I also index it by this symmetry parameter epsilon. Well, if there is a b such that the variation of the action evaluated for this variation delta epsilon is a boundary term, then we have a symmetry of the theory. So now we can put these two statements together. So the first one is that the on-shell variation of the action is a boundary term. The second one is that if we have a symmetry, then the variation of the action under this symmetry is at most a boundary term. Possibly this boundary term is 0. This is also allowed. Well, then from this, we can simply deduce a conserved quantity, namely this quantity q, which we just defined to be, so capital Q, so p delta q minus this boundary term, where you should note that delta q is now the variation delta epsilon. Well, now by putting these two equations together, you see by construction that on shell, this quantity is conserved. So we have associated to a symmetry a conserved quantity Q, which typically at this stage we call the Noether charge associated with this symmetry. Now, what is also very useful, and what we will see very explicitly in the case of gauge theory, because it gives us lots of important structure, is that there is an inverse Noether theorem. So this inverse theorem simply tells us that if we consider a conserved charge, so I'm using sort of Hamiltonian notations here. So I have position Q, momentum P. It's possibly a time-dependent charge. So a conserved charge, if it's time-dependent, it means that I have to compute the Poisson bracket with the Hamiltonian and also the partial time derivative. Well, then the inverse theorem tells us that if we have such a conserved charge on phase space, the following two transformations, delta epsilon Q and delta epsilon P, which are defined by these Poisson brackets, define a symmetry of the action. So this we can just prove by putting a general form of an action in Hamiltonian form by a Legendre transform, and then plugging these transformations inside of this form of the action. Now, the other important result is that the set of all conserved charges for a theory forms a Lie algebra with a structure constants, which I callCijk here. So I just say this because we want to keep in mind the generalization of this result to gauge field theories. So this should be familiar. A simple example, for example, where this is very useful is in mechanics. We can choose, for example, one example which is nice is the conformal particle. So it's a particle with a 1 over q squared term. And here I'm just listing simple symmetries and the conserved charges associated with these symmetries. So the first symmetry is just time translation invariance. And note that for this symmetry, I mean, for both symmetries which I discuss, I present them in finite form and also in infinitesimal form. So now looking at the infinitesimal symmetry, I have written the equivalent of this boundary term B, which I mentioned on the previous slide. So for time translations, this boundary term is 0. And also infinitesimal time translations act in this way on the position Q. So delta epsilon Q is epsilon Q dot. And then applying Noether's theorem, we derive a conserved quantity, which is nothing but the Hamiltonian or the energy of the system. Now, for this particular example, the reason I chose it is that there is another interesting symmetry, namely a scaling symmetry, which is given here on the left in finite form and in the middle column in infinitesimal form. And again, by applying Noether's theorem to this scaling symmetry, you can derive a conserved quantity, capital Q. Now, this is very useful and interesting because in this example, these two conserved quantities E and Q enable you to completely solve the dynamics of the system and reconstruct the trajectory of the particle as a function of these two conserved quantities and time. Now, I just want to mention this because we also see in this example something which will kind of resurface in a more sort of fancy way later on in other examples, which is that on the phase space of this theory, we can actually build a third conserved quantity, which I call here, which people usually call K, but which is not actually independent from the first two conserved quantity E and Q. But even though it's not independent, it's actually very useful because it leads to interesting algebraic structures on the phase space. In particular, I invite you to check that under the Poisson bracket, the conserved charges E, Q, and K form an SL2R algebra. And the last remark which I want to make, which is also why I wanted to choose this example, is that notice that here, although the finite form of the symmetries acts on the coordinates, so this is manifest for the time translation, but also very manifest for the scaling symmetry. Usually when we apply Noether's theorem, especially when we go to the infinitesimal form of the transformation, it's much more useful to trade these transformations of the coordinates for transformations acting purely on the fields of the theory. Because especially if we keep in mind that we want to go to general relativity, we don't want to think of symmetries as transformations involving the coordinates. because coordinates are something which we should be able to choose freely. What is physical is the field content of the theory. So it's always useful to write explicitly the symmetries as acting only on the field content of the theory, which is what we did here to compute these Noether charges. So this is just a first lesson. Well, now we can easily go to field theory. Again, this should be familiar material. So in field theory, once again, by applying the same two ingredients. So the first ingredient is that the unshelled variation of the action is a boundary term. And the second ingredient is that if you have a symmetry, it should leave the action invariant up to a boundary term called B epsilon. You see, the only difference is that now I have a covariant mu index appearing in this object J. And now Noether's theorem tells us that this quantity J is a conserved current. Now, if we integrate this, this space-time conservation law and isolate the time derivative on the left and the spatial gradient on the right, and then we use Stokes' theorem, we get that the time evolution of the quantity, or the integral over a three-dimensional volume of the time evolution of the zero component, the time component of this conserved current, is equal to a surface integral. So if this region has no boundary, or if we choose suitable boundary conditions, we can then extract a conserved quantity, which is the integral over the spatial region of the time component of this current. So this gives us our conserved quantity. So a familiar application of this is to look at Maxwell theory, for example.
Marc?
Yes?
There is a question about the symmetry associated to K.
Yes. On the previous slide?
Yes.
Yes. So in fact, the symmetry associated to K is just a combination of the symmetries associated to time translations and scaling symmetry. This follows from the fact that this charge is not independent from the other two charges. So the symmetry is just a composition of the symmetries generated by E and Q, as we can check. So if I go to Maxwell theory, just to finish with this example of field theory, I'm already jumping a bit ahead of myself now, because you see that when I consider these variations of the Maxwell gauge field, delta epsilon, I'm actually combining two types of variations. I'm combining a Lie derivative, which is the second term with a minus sign, and I'm also combining a gauge transformation. This is a trick which is usually done in Maxwell theory, because we want to have a variation which is a gauge invariant quantity. So you see indeed that by defining this combination of space-time transformations and gauge transformations, we get that delta epsilon of A is proportional to the field strength F. Using this transformation, you can show that, as expected from a symmetry, this transformation leaves the Lagrangian invariant up to a boundary term. Now we see again something which is should be familiar from field theories, is that from this symmetry, we can actually construct a conserved current. And actually, even more generally, we can associate to this symmetry an energy momentum tensor, which happens to be symmetric, gauge invariant, and traceless. So this is just a computation of this conserved current J mu. And once you compute this, you identify this, energy momentum tensor. So the reason why you have such an energy momentum tensor is that you want to be able to conserve quantities. But for example, you know that if you are in 4 space-time dimensions, there should be more than just one conserved quantity. This is the reason for which you actually have a whole energy momentum tensor, and you have several vectors which are conserved, several quantities which are conserved. For example, if you focus on time translations, you get this current JT, and the time component of this current JT is the integral over a volume of T00, and this is just the charge associated to this is just the energy of the system, as you can see here. It's just the total Hamiltonian. So just as an exercise, you can also show, and I just mentioned this because it's another peculiar feature sometimes of symmetries and theories, you can show that at the classical level, this equation this formula for the current and the conserved quantity actually extends to the whole conformal group. So instead of considering epsilon, which is a constant, you can actually consider vector psi of x, which satisfy this conformal Killing equation. And as long as this conformal Killing equation is satisfied, then you have symmetries and conserved quantities. And the reason I mention this is that these conformal symmetries are famously broken in the quantum theory, even though they are present in the classical theory. So now we covered the familiar examples. We want to move on little by little to gauge theories. So for the moment, the Noether symmetries which we have discussed, so of course, modulo the slight fact that I already used gauge symmetries to discuss the Maxwell example, but the Noether symmetries in the mechanical case, we can think of them as being labeled by global symmetry parameters epsilon. And I just put global between quotation because you will see in this talk that in this set of lectures that we have to be a bit careful with the word global because it can have a very different meaning depending on the context in which we use it. So here I mean global in the sense that the parameter does not depend on space-time. So now for gauge symmetries, the parameter can be local in time. For example, if you have a gauge mechanical model, such as this example Lagrangian. And of course, the familiar gauge theories have a gauge parameter which is local in space-time. So it can depend on the coordinates. So what we also know from kind of the usual Hamiltonian structure of gauge theories is that when we have a gauge theory, as we will see again, there is a particular relationship between different phenomena, different notions of different manifestations of these gauge symmetries. So the relationship is between gauge symmetries, identities between the equations of motion of the theory, also the fact that the theory has undetermined or underdetermined variables, and also the fact that the theories these gauge theories have what we call first-class constraints. And these first-class constraints are precisely, in Hamiltonian language, the generator of the gauge symmetries. Now, without having details for the moment, if you just try to compare Noether symmetries to gauge symmetries, well, for a Noether symmetry, we have already seen that we have a charge Q, which is a non-zero quantity. We have a parameter which is constant. This charge Q is conserved in time. And by Poisson bracket, it generates a variation delta epsilon Q, which is the symmetry of the theory. Now for a gauge theory, we see that if we just naively make the analogy, this kind of completely fails because for a gauge theory, because of the relationship that I mentioned above, the symmetry is generated by a constraint. And this constraint is this curly C, which depends on the function of space-time epsilon of x. And this constraint is vanishing on shell. So this constraint being vanishing on shell cannot be the equivalent for a gauge symmetry of Noether's charge, which we called Q earlier. So we have to find what replaces the Noether charge in the case of a gauge symmetry. So the question that this raises, what we want to understand, what we want to do, is to understand if Noether's result applies to gauge symmetries. Of course, you will see that this is related, for example, in general relativity, to the very definition of energy. Because in the simple mechanical examples which we quickly reviewed, the quantity associated to invariance under time translations is, of course, the energy of the system. If we don't know how to construct such quantities in general relativity, a priori, we don't know how to define energy in general relativity. This is a complicated and subtle task to do, but what we want to understand is the tools to actually at least try in principle to compute a meaningful notion of energy in general relativity. So the punchline, the conclusion of the introduction, so as I will try to show you, you will see that in a field theory, or in a gauge field theory, when you have a boundary precisely has the ability to transform a gauge symmetry into a Noether symmetry. So out of a gauge symmetry to which a priori you can only associate a constraint, which is vanishing on shell, we will actually be able to extract a quantity Q, which is a charge in the sense of Noether and which is not vanishing on shell. So you can think of it in these terms precisely, that a boundary may, in certain cases, turn a gauge symmetry into a Noether symmetry. And again, maybe this is a poor choice of words. I don't want to confuse you because sometimes, you know, people maybe, I mean, okay, we have to be a bit more precise about what we mean by this statement. So that's our goal, is to clarify the meaning of this statement. Yeah, so now what I chose to do is to give just a few elements of bibliography at the end of each section. So now it's the end of the introduction. So I just want to mention this nice review by Max Bañados and Reyes about mechanics and Noether's theorem and gauge symmetries and boundary terms. And of course, there is a much longer reference, which is well known. It's the book by Hainaut and Teitelbaum. So I invite you to check these references, at least for this introductory section. So now we move on to the more technical part and to the core of the topic, which is first to introduce some formalism, and which we will use in the rest of the lectures. And this is the so-called covariant phase space formalism. So first, we have to agree on a few notations and conventions such that we can actually efficiently use this formalism without making mistakes. And also, my goal here is to, I mean, as I mentioned, there's many work on this topic, and people usually use different, sometimes slightly different formalisms and notations. So my goal is to just choose a story, explain the story, and then you should be able to go and compare with other formulations of the same mathematics. So notations and conventions. So first, for space-time indices, we will try to use as much as possible familiar differential forms. So this means that, of course, we will use an exterior derivative, which maps P forms to P+1 forms, and also an inner product, which I just choose to denote by this corner here, or this hook, which maps P+1 forms to P forms. And so just so that we are clear on this, and you will see in a minute why I mentioned this, because I want to make an important analogy. If you contract, for example, a vector xi with this inner product with a 2 form, A wedge B, well, if you contract a vector with a 2 form, we get a 1 form, which is why on the left this has an index mu. And then this 1 form is defined by this anti-symmetrized contraction on A and B. So now, as I already argued with the example of the conformal particle, what we said is that it's always best to think of symmetries as acting on fields and not as acting on the coordinates. We want to forget the coordinates once and for all. So for this, we want to be able to manipulate variations of the fields themselves, because the fields are the quantities which transform under the action of symmetries. So we want to have a framework and tools to manipulate variations of the fields and say that the variation of a field is a symmetry. So to do so, by analogy with the structure on space-time indices, we want to introduce some structure on the space of fields. So again, 2 structures, well, simply a derivative and an inner product. So the derivative on field space, we have already encountered it. It's just what we have called delta. So we can think of this derivative on field space, delta, as mapping an F form in field space to an F+1 form in field space. We will give examples of this in a minute. And then again, just by analogy for the notation, we will have an inner product on field space. We will see in a minute how to use this inner product. And just, I apologize for the notation. I just choose to call this inner product with this, this double hook. And this inner product takes F+1 form in field space and returns an F form in field space. So just thinking now by analogy with what we did above for space-time indices and differential forms, we can now think of a gauge transformation as a vector field in the space of fields. So if we do so, we can use our inner product to actually contract this variation, which we can think as a vector field, with a field space 1 form, which is delta of this field psi here. And if we do so, we obtain a field space 0 form, which is just the variation of the field psi given by the transformation delta epsilon. Now we can generalize this to the contraction of the variation delta epsilon with a two form in field space. So this two form in field space, I have two fields now, and the two form in field space is, for example, delta psi times delta of phi. And of course, as a two form in field space, these variations, you can think of them as being anti-symmetrized, just like for usual familiar differential forms in space-time, meaning that if we contract now the variational vector delta epsilon with this field space two form, well, you see in the middle, I first have to hit on the first entry and then minus, and I hit on the second entry. And of course, because delta psi delta phi is a two form in field space, it is anti-symmetric. So you see between the first, so the first term and the third term, I have just switched the place of delta phi and delta psi, and I pick up a minus sign in front. So just as a word of caution and to kind of remove this ambiguity from now on, I just want to state that of course, for these lectures, I'm not trying to be extremely mathematically well-defined, and I will give you references if you're interested in this, in the precise definition of this mathematical structure. But for example, to be extremely precise, we should define these variational vector fields, which we contract with forms in field space in terms of these functional integrals. So to be very precise, I should define this capital X indexed with epsilon, and then acting with this on the variation delta psi, this will give me then what I call delta epsilon of psi. But I don't want to carry these heavy objects and to kind of get lost in this, in something which is too abstract. So I want to kind of make it a bit simple and minimalistic to have just enough for what we want to do. So now in principle, we are equipped with structures to actually manipulate objects which have a dual nature. So what I mean by this is that now we can manipulate objects which are P forms in space-time, but also F forms in field space, because these objects may have field variations. So we'll refer to these objects as P, F forms. So the last point about the notation which I should mention is that, of course, these two derivatives, they square to 0. So d square is 0, delta square is also 0. The only thing which you have to specify, and which may differ from reference to reference, is that here I choose for convenience these two derivatives, so the exterior derivative and the derivative on field space, to actually commute. You could also choose them to anti-commute, but okay, I just choose them to commute. And okay, the last word of caution is that, of course, people use many, many different notations for this, and there's no, I think, reason to, I mean, one is not superior to the other. So just keep in mind, if you read other papers, it's very common, of course, for the space-time contraction to use the small inner product I. For the field space contraction, people use sometimes a big inner product curly I. And then also for the wedge product, sometimes people use a double wedge product or a curly wedge product to indicate a wedge product between field space forms, but I want to refrain from doing this. So the last word now before we move on is to just mention that this is, of course, due to the work of many, many people. In fact, too many people to even cite. There's maybe even references which I'm not aware of. But I will come back to this at the end of the lecture in the last chapter, which I call the advanced topics. So here for the moment, I just want to introduce this covariant phase space formalism, following what is sometimes called the Geiller-Wald version of the formalism. So again, depending on where you try to learn this, you may see some differences. I will try to highlight the differences when they appear, but in order to make things as simple as possible, I will try to follow one special road, and this is the so-called Geiller-Wald covariant phase space formalism. Okay, so now we can start. So with the basic ingredients. So we're basically trying to repeat what we in a sense already said about in the introductory chapter, but trying to use this notion of this this variational calculus on the space of fields. So again, we start with the Lagrangian of a theory, which may depend on an arbitrary collection of fields. So these fields, capital Psi, may be a scalar field phi, it can be a gauge field A or a metric G nu nu, depending on what you're interested in. Now, to also discuss this once and for all, even though we will come back to this at the end of the lecture, we also have to keep in mind, and of course we know that when we study a theory, sometimes we specify the theory not only with the Lagrangian, but also with a possible boundary term. Typically, the boundary term is here to control the choice of polarization. So what we keep fixed or what is allowed to vary on the boundary. So this is, of course, what we call the boundary conditions. You will see that these boundary terms can also be related to methods of renormalization of the phase space. So I want to keep track of the boundary term in the beginning and then tell you why they disappear. And at the end of the talk, if we have time, we will see how, in a certain sense, we have to be a bit careful about these boundary terms. So now we can kind of be a bit formal and do what we already did. We compute the variation of the Lagrangian of the theory. And now the Lagrangian is L plus the boundary term, D of little l. And then, okay, it's a familiar thing. When we compute the variation, we want to isolate the equations of motion. And once we isolate the equations of motion, we produce a boundary term, theta, which will add to delta L, which was the initial boundary term in the Lagrangian. So now this object theta, it's the first time, at least with this now formal layer of notations, it's the first time that we encounter an object which is D minus 1, 1 form. So D here is the dimension of the spacetime. So since theta appears as the boundary term here, when I do integration by parts, this is a D minus 1 form in spacetime. But you see that the variation in this equation star is actually hidden inside of this object theta. So this theta itself contains a variation. So because of this, it's a one form in field space because it has a single variation of a field. And this object, it's very important, so we give it a name. It's called the Pre-Symplectic Potential. Pre-symplectic, you will see the reason for which we call it pre-symplectic in a moment. The reason is that the symplectic structure at this point may have 0 directions. So because of this, we cannot promote it to a symplectic structure, and we call it pre-symplectic. And usually, probably I will drop altogether the term pre-symplectic and just refer to theta as the potential, or at least the symplectic potential. Okay, so now from this symplectic potential theta, what we typically do is take a second field variation and construct a symplectic current out of this potential. So the current now, we haven't changed the form degree in spacetime, so it's a D minus 1 form. But since we take a new variation, we get a 2 form in field space. So this is a D minus 1, 2 form. You see that if we act with a further variation on the boundary term in the equation star, well, the delta square of L drops because delta square is 0. So because of this, you see that immediately in the first step of our calculation, we get rid of the boundary term, and the boundary term will not play a role from now on. So we can forget about the boundary term. Now what we want to realize is that if we stare a bit at equation star, which is the variation of the Lagrangian, so it's an equation which relates the variation of the Lagrangian with the equations of motion and the exterior derivative of the potential theta. If we look at this equation, we see that if we take the exterior derivative d of the symplectic current, which is delta of theta, we get that on shell, d of delta theta is vanishing on shell. So hence, again, this weak equality means when I impose the equations of motion. So you can see that this holds by looking at this variation equation star. So if this is vanishing on shell, and since this is a total exterior derivative, we can actually imagine integrating this quantity over a d-dimensional manifold, which is bounded by 3 quantities. So I choose my d-dimensional manifold M to be bounded by 2 hypersurfaces, sigma 1 and sigma 2, and also what I have represented here on the drawing by a time-like surface, which I called here B.
Marc?
Yes?
I think there was a question about someone who wanted a bit more explanation on star. The equation star, I mean.
The equation star?
Yeah.
Yes, so the equation star is the variation of the Lagrangian. And I have written it here in a way that makes explicit the fact that when I vary the Lagrangian, well, typically, usual, I mean, all theories that we know of have derivatives of the fields in the Lagrangian. So when we want to isolate variations of the fields to read the equations of motion, we have to do integration by parts. And if you want to put the variation of the Lagrangian in the form equations of motion times the variation of a field, we have to, again, do an integration by parts, and this isolates a boundary term. And this boundary term is precisely for us what we call the presymplectic potential. You will see on the examples that come next that, that theta just very easily, and in a sense by construction, tells us what are the conjugate variables in the phase space of the theory. So more precisely, the current tells us what are canonically conjugated variables in the theory. So I'm not sure this. And yes, I see in the chat that the equation of motion is. Yeah, so maybe the equation, maybe the star is misleading because I put a wedge. Okay, this is my fault with the notation. I put a wedge between equation of motion and delta phi, but delta psi. Delta psi is here. I mean, it kind of depends on the theory that you have. Maybe at this stage, it's just a notation. I'm assuming that everything is written in differential forms, so I can isolate equations of motion wedge delta psi. But maybe you write a theory which is not in terms of differential forms, and then it doesn't take precisely this form with the wedge product, but at least schematically it's of this form. It's the equations of motion times a variation of a field. So hopefully this will become clear with examples in a minute. So what we just wanted to do at this stage was to integrate this quantity, d of delta of theta, which is vanishing on shell, integrate this over a d-dimensional manifold, which is sigma 1 union sigma 2 union the boundary B. So if we do this, because this is vanishing on shell, we get this equality here, which is written on the right of the picture. And now we see that if we allow ourselves to impose a condition, which we will go back to in a few hours, maybe tomorrow, we'll try to understand what is the meaning of this condition. But here I refer to this as a flux condition. So meaning that if there is no flux through the time-lag boundary B, so you should understand this as the condition that the integral over the boundary B of delta theta is 0. Well, you see from this equality that if this quantity, integral over B of delta theta, is vanishing because, for example, of your boundary conditions, or because of the physics of the system that you're studying, well, then you get that the integral over sigma 2 of delta theta is equal on shell to the integral of delta theta over sigma 1, meaning that the integral of delta theta over a hypersurface sigma is actually conserved in time. And this quantity, we call it the presymplectic structure. And since we have integrated the presymplectic current over a d-1 dimensional manifold, we get a 0 form in space-time. But you see, there are two variations here. There is a variation inside of the potential and a variation in front of the potential. So because of this, this quantity is a 2 form in the space of fields. So this quantity in orange in the box here is the presymplectic structure of the theory. So generically, if we think a bit about this vanishing flux condition, and again, we'll come back to this a bit later because it's very important. You see that generically what can happen if you want to be a bit explicit about the various cases which we can encounter. Generically, what we may have is that on this time-like boundary B, we have that theta plus delta L, the boundary Lagrangian which we started with, is possibly equal to D of something plus what we call a flux term. So you see that if I assume that the right-hand side is 0 here, if DC is 0 and if the flux is 0, the fact that theta plus delta L is vanishing on B is just the requirement that I have a well-defined variational principle. Because of course, here I have written everything in terms of variations of the Lagrangian, but what we're really interested in when we derive the equations of motion is the variation of the action. And to extract the equations of motion, we have to ensure that in the presence of boundaries, the action is a functionally differentiable quantity. And because of this, we have to discuss the fate of the surface integral, which appears when we integrate by parts the variation of the action. And this is typically addressed by the choice of boundary conditions. So yes, so this is just to say that generically, this quantity theta plus delta L on the time lag boundary can be d of something plus a flux piece. The d, C, I call it C because we usually call this a corner piece. And this corner piece, if you think in terms of dimensionality of these manifolds, so you see theta is a d-1 form in spacetime. So C is a d-2 form in spacetime. So d-2 means codimension 2 form in spacetime. So usually we refer to these terms as corner terms. And on the little spacetime picture, this corner term is the purple circle S, which is both the boundary of sigma 2, sigma 1, and B. So essentially, physically, but again, we will try to make this much more explicit, understand what is happening here physically. Essentially, if the flux is non-vanishing, it means that we have an open system and that there are degrees of freedom leaking away from the region on which we're focusing. So for the moment, we want to assume that this is not the case and assume that we have a well-defined conserved presymplectic structure, which we call capital omega. Now the question is what we can extract out of this conserved symplectic structure. So for this, we will look one last time at Noether's theorems. And now you notice that theorem is all of a sudden plural because we will encounter a second Noether theorem, because the one we have mentioned so far is actually only one of Noether's 2 theorems, precisely because the second one applies to gauge symmetries, which we are now precisely discussing. So again, to be very explicit about the notations, we'll consider gauge transformations with a parameter, which generically I will denote epsilon, but this can be kind of a different type of object depending on the gauge symmetry which we're looking at. For example, if you're looking at symmetries of the metric, this is typically a diffeomorphism acting by Lie derivative. So this parameter is a vector field psi. If we are in Maxwell theory or in Young-Mills, we're looking at gauge transformations. This is a gauge parameter alpha. So for the moment, and it's also something which we will have to understand and be very precise and careful about, we will assume that this parameter epsilon does not depend itself on the field content of the theory, meaning that these variations in field space, delta, they vanish when they act on the parameter epsilon. Now we go back to this variational formula, which we had earlier. So again, if the variation is general, this is just what we had on the previous slide. So the fact that the variation of the Lagrangian is a piece which is just the equations of motion, where we have isolated the variation of the fields. And when we isolate the variation of the fields, we produce a boundary term, which is the symplectic potential theta. And now in this variational formula, we can do what we did on slide 1, when we did the first mechanical example. We can, of course, take the variation to be a gauge transformation delta epsilon. So now by definition, if this is a symmetry of the theory, this can produce at most a boundary term. So this produces in the last equality a boundary term B. So we get delta epsilon of L equals dB. So this is just using our familiar variational formula and the fact that the requirement that epsilon is a gauge transformation, is a gauge symmetry. Well, now Noether's first theorem, which we can rephrase now in its, in a sense, in its most general formulation, tells us that there is a current, which is a d-1, 0 form, J, and that this current is closed on shell. And because this current is closed on shell, we write this current J as the exterior derivative of the Noether charge Q. So two things are important in this red statement of Noether's first theorem. The first thing is to notice that indeed this current is a d-1 form in space-time, but it's a 0 form in the space of fields. And it's a 0 form in the space of fields because in this variational formula, we used it by replacing all the field variations by a gauge transformation. So now we don't have 1 forms in field space anymore. We have specified these arbitrary field variations. We have specified these 1 forms to be of the precise form of gauge transformations. So because of this, this Noether current J is a 0 form in field space. And again, this variational formula of the Lagrangian tells us that dj is vanishing on shell. So we can write J as d of q and call this from now on the Noether charge. Now the second theorem, which we encounter now for the first time, at least in these lectures, the second theorem precisely has to do with gauge transformations. And it's very beautiful because it tells us something very striking. It's what we mentioned a bit earlier. We said that for gauge theories, there is a relationship between all sorts of structures. So namely the fact that we have gauge symmetries, the fact that we have first-class constraints, the fact that we have undetermined variables in the theory, and the fact that there are relationships between the equations of motion. And precisely this last fact, the fact that there are relationships between the equations of motion, is this Noether second theorem, this Noether identity, which tells us that if we take this, this piece of the variation of the Lagrangian, so the equations of motion times the variation of a field, if we evaluate this variation on a gauge transformation, we get off shell exactly without using the equations of motion, otherwise this would trivially be 0. We get off shell a boundary term. This boundary term, I just choose to call it P, and just for convenience, I put a minus sign in front. We could of course change P to minus P, this would be the same. So you can think of this P as being the off-shell contribution to the Noether current. So the first theorem identifies the charge Q, which is a d-2 form, so a codimension 2 quantity. This is a quantity which is identified on shell. And the second theorem, because we are dealing with gauge symmetry, identifies the off-shell piece of the Noether current. So the final result, applying the two Noether theorem, tells us that the Noether current J is an off-shell piece P plus D of the Noether charge Q. Of course, for the moment, we don't really see or understand physically what this means because we have just, well, constructed the quantity J, and this J is expressed in terms of P. And since we don't really know what P is, it just seems that we have, taken one name on the left and given it another name on the right. Of course, we will see on the next slide what is the physical interpretation of this quantity P and of the quantity Q. Now that we have this at our disposal, we can ask the question which we were kind of, which we wanted to ask from the beginning, in fact, which is the question of the charges of the theory. So there is already a notion of charge here because above I have called Q the Noether charge. But now we will make an important difference and we will talk about Hamiltonian charges. And you will see, so the goal of this section here is to explain the important difference which exists between the Noether charge and the Hamiltonian charge. So just schematically at this stage, since in fact the symplectic structure which we have introduced earlier, so the conserved symplectic structure capital omega, is in fact of the form, if you just think again, if you think about mechanics, this is just of the form delta P times delta Q, where P and Q are conjugated variables. Here just schematically I've removed the integral over sigma. So just again thinking schematically, if this is the symplectic structure, well, by definition, the Hamiltonian generator of the gauge transformation delta epsilon. So this is a function on phase space, curly h of epsilon, which by Poisson bracket acts on Q and produces the variation delta epsilon Q, which is supposed to be a symmetry of the theory. Well, now since we have this field space calculus, which we introduced a few slides ago, we can actually construct this generator h of epsilon by computing a contraction of the gauge transformation with the symplectic structure. Because you see, if I compute, if the symplectic structure is of the form delta p wedge delta q, or sorry, delta p times delta q, then this is a two form in field space. And if we use the rules of the field space calculus, which we had before, you see in the middle, if I contract delta epsilon with delta p times delta q, I get what is on the left-hand side. And now the Poisson bracket by construction tells us that the action of this on Q is delta epsilon of Q. So this means that once we have the symplectic structure at our disposal, and this notion of contraction of a variation of a gauge transformation with a field variation, we can construct the generator of the gauge transformation. So what we want to do is compute this carefully now. For the moment, this was just a bit schematic, and just to convince us that this can work, we want to compute this very carefully for various different theories, and also use examples to actually convince ourselves that this is indeed doing what we are saying it's doing, namely giving us the Hamiltonian generator of gauge transformations. So to compute this carefully, we have a full slide on the Hamiltonian charges here. And so I'm sorry, because I realize now I should have put maybe pauses between these various equalities, because I wanted to unfold them step by step, but okay, here is the full reasoning. So the first line, of course, is that we want to define, compute this quantity, which is the symplectic structure contracted with a gauge transformation, with a variation, which is a gauge transformation delta epsilon. So I'm using the definition of the symplectic structure. This is the integral over sigma of the symplectic current, which is delta of the symplectic potential theta. And now I have a minus sign for convenience. This is what I had here on the previous slide. You see the bottom equality that there is a minus sign. This is just because of how we define the Poisson bracket. And now I want to compute the variation, sorry, the contraction of delta epsilon with the symplectic current. Now again, so to go from the second equality to the third one, we use again just these rules of contraction of variations with two forms in field space. And you see that, of course, delta of theta is a two form in field space. So there is a variation in front, and there is a variation inside of theta, which is why I wrote theta of delta. So now the third equality, I replace these two variations, one after the other, and I anti-symmetrize. Now from the third to the fourth equality, I go back to the definition of on the previous slide of the Noether current. So the red definition here of the Noether current is that J is theta evaluated on delta epsilon minus the boundary term. Now, if I use this in this equality, well, I get the fourth line. Okay, sorry. And now to go from the fourth line to the fifth line, I use the fact that J, what we have just shown before, J is a piece P plus a boundary term Q. So the piece delta J produces delta P integrated over sigma, and a boundary term, which is delta Q, integrated over the boundary of sigma, which I call S. Now, the last thing to notice is that for the last equality, I've just did a bit of rewriting for the last equality. So in the last step, I have just assumed that that a certain quantity is zero. This certain quantity is the gauge variation of the term which is equation of motion wedge delta psi. You see, if you assume that this is zero, you can I'm just showing it on this equation below. You can show that the bulk term, which is delta B plus a gauge transformation of theta, you can show that this is a boundary term, which I call F. So I just wanted to use this to show that the final result, which is that the contraction of a gauge transformation with the symplectic structure is an integral over sigma over the spatial hypersurface of delta P, which is the off-shell piece of the Noether current, plus a boundary term. And this boundary term is the variation of the Noether charge, plus a term which I call F here. So there are two things to see from this result. The first thing is that, again, we have just shown before that P is precisely the off-shell piece of the Noether current J. So by construction, this quantity P is vanishing on shell. So you see that what we're calling now the generator of the gauge transformation, so this function on phase space H of epsilon, which we have obtained by contracting a gauge transformation with the symplectic structure, if we evaluate this on shell, the bulk piece, so the integral over sigma, completely drops. And this is because the bulk piece is given by delta P, but P is the off-shell part of the Noether current. So this is 0 on shell, and on shell it drops. This means that on shell, the only thing you're left with, when you compute the generator of this gauge transformation, the only thing which you're left with, the only non-trivial information is encoded on the codimension 2 boundary S. Which is why we already understand at this point that if we had kind of repeated this calculation without the boundary for our spatial slice sigma, without the boundary S, so without this codimension 2 boundary S, we would not see any generator associated to this gauge transformation. We would not see any non-zero, any non-vanishing quantity. We have to have a boundary in order to see this, because when you're on shell, the only thing that is left is precisely a boundary term. So this is what I say here, that on shell, we are potentially left. Of course, it may be that this term itself is completely identically vanishing. But potentially, on shell, we are left with a boundary term. So just for terminology, I don't like to use this term, but sometimes this is what people refer to as improper gauge transformations. Precisely because they are generated by a quantity which is not, strictly speaking, a constraint, because it's not vanishing on shell. Now, the last thing we have to be precise about, there is a slight technicality, but something which is very important, is that you see that I introduced a bit secretly, without really mentioning it, a notation delta slash. So this quantity which we computed on this slide, so the contraction of a gauge transformation with the symplectic structure, I call it delta slash of the generator H. And this is delta slash because we're not yet guaranteed at this point that we can write this in the form of a total variation. We are not guaranteed that this is really of the form delta of something, so that we can integrate this quantity with respect to delta in field space. And you can see this on the equality which we have derived here in this whole slide, because you see the first piece in the bulk is delta P. So this is fine because delta is in front. On the boundary, the first piece is delta Q. That's fine. But the third piece contains a delta hidden inside of it. And I'm not guaranteed that this is of the form, that this is an exact form, delta of something. So precisely because of this F piece here, we're not guaranteed that the generator H exists as a finite generator on the phase space. And now the other thing maybe which I wanted to mention on this slide is that, again, you see from this formula, but we will do an example in a minute, it will become clear. One can see here that kind of contrary to what the name suggests, the Hamiltonian generator of these gauge transformations delta epsilon is a priori not only given by the Noether charge. Because again, what we, at least here traditionally, we call the Noether charge, Q, is not the only piece which appears on the boundary. It's not the only quantity which survives when you evaluate this generator on shell. Because you also have the piece F, which may be non-vanishing and may even be non-integrable. So we have to discuss the fate of this piece F, understand what it does and what happens to this piece in different theories, how we can manipulate it, and what it does to the theory. This is what we have to understand. Now we can just do explain a bit the interpretation of this result. So hopefully okay, I don't know if I went too fast. Hopefully the derivation of this identity was clear. I just apologize for the so for the proof that the bulk piece delta B minus delta epsilon of theta is written as a boundary term. We will repeat this proof in the case of general relativity in a minute. So we will see what happens to this piece in a minute. You don't have to assume what I assumed here, that delta epsilon of the equation of motion term is identically vanishing. You don't actually have to assume this. It was just easier on this slide to assume it to get immediately F on the boundary, but you don't have to do this. You will see this in one or two slides. So now, what is the interpretation of all these structures which we have constructed? Yes.
I think it's like, let's do a small 1 minute break.
Okay, maybe it's
before.
Yes. Okay.
So yeah, if people want to take like 1 minute break, and we will start in like 1 minute again.
You scared me, Christophe. Je pense. Je ne pas toutes les possibilités sur l'interprétation. Est-ce que ce serait pas relié? C'est pas une question hyper importante pour le. Bon.
Marc?
Yes, I'm back.
Well, there is a question.
Yes.
Someone asking why on the last slide did we say P equals 0? Second last point.
So this slide here?
Yeah, I think.
Yes, because sorry, I forgot to mention this. So this whole covariant phase space formalism is an on-shell formalism. In fact, is a set of structures on the space of solutions of the theory. So once we integrate this quantity H, P is vanishing on shell, and therefore, if you evaluate this on shell, you won't see this contribution. So because we're interested in computing these quantities on shell.
Okay.
Okay, good. So maybe if we continue. And
you have, I think, around half an hour before the question time.
Yes. So now I apologize if this was a bit formal or abstract. We want to give an interpretation of these quantities and understand what we learned and apply it to examples. So the interpretation. the first interpretation is that if the object h of epsilon exists, for the moment, as we said, we're not guaranteed really that this object exists, because there is a, in this piece which I called F, there is maybe, we have to be careful, a field variation which is hidden inside. It's not clear that we are allowed to pull this field variation outside of this expression. But if we can do so, and there are examples of theories for which you can always do this, we will also see examples of this. If you can do that, so if the generator H exists, well, precisely then H by construction, you will see, is the Hamiltonian generator of the gauge transformation delta epsilon. So sometimes people say that the vector field delta epsilon is Hamiltonian on phase space. Now the bulk piece of the constraint, so sorry, the bulk piece of the generator, which is, so someone asked the question, it's the piece which I set to 0 when I go on shell. Well, this bulk piece, if you're familiar with the Dirac Hamiltonian analysis, you have already encountered it, because it's precisely the constraint, what you call the constraint or the gauge generator in Dirac's Hamiltonian formulation. So I have just rewritten here this bulk piece. So it's an integral over sigma of this quantity P, which now, because of another result which we derived, we know that P is also the off-shell piece of the neutral current. So P depends on the field parameter epsilon. So typically this constraint is defined as an integral, so a smearing of a quantity P with space-time dependent parameters epsilon. It also depends on the fields, and importantly also on variations, derivatives of the fields. And precisely this quantity P, I have chosen the name curly C here because this is the constraint. So the gauge generator of Dirac's Hamiltonian analysis. So if you are not using this covariant phase space formalism, but doing kind of standard Hamiltonian analysis of the theory, you would find that the Hamiltonian generator of the gauge transformation is given by C. But this is precisely where the subtlety lies. And this is precisely what the advantage of the covariant phase space formalism and what we gained by using this slightly more abstract formalism instead of using usual Dirac Hamiltonian analysis. What we gained is that, so again, let me just remove this point here, sorry. So suppose you want to actually check that this quantity C, so this constraint, which is an integral over sigma, is the generator of the gauge transformations delta epsilon. Well, to do this, you want to act with Poisson brackets, but basically you have to satisfy the same requirement as for the action of the theory. Namely, to be able to act, this quantity, which is an integral over sigma, has to be functionally differentiable. Just like the action has to be functionally differentiable to be able to extract the equations of motion. So you have to deal with the boundary term which appears. You typically do this by imposing boundary conditions. The same thing is true for a codimension 1 integral over sigma. If you want to treat this as a Hamiltonian generator acting by Poisson bracket, this quantity C has to be functionally differentiable. And because C typically contains derivatives of the fields, when you compute the variation, you have to again integrate by parts to isolate the variations, and you produce a boundary term. And this boundary term spoils the differentiability of this constraint or this naive Dirac generator. In fact, we can very easily check this, for example, with the Gauss constraint of electromagnetism. So I'm calling this constraint a curly G, like the Gauss constraint. And just in very light differential form notations, this Gauss constraint is the integral over a gauge over sigma of a gauge parameter alpha times the divergence of E. Now it's clear that if we take the field variation of this quantity, well, just because there is a derivative of E, we have to integrate by parts and we produce a boundary term. And again, as we said, because of this boundary term, this quantity G, the Gauss constraint itself, is not functionally differentiable. But the differentiable generator is precisely, and by construction, what we have obtained on the covariant phase space by computing this contraction of the gauge variation with the symplectic structure. In fact, using this covariant phase space calculation is a neat way, an automatic way to subtract from the variation delta G, which is on the left, to subtract the boundary term, which is on the right. And if you subtract, you see this equality here, if you subtract the boundary term on the right and put it back on the left, you are left with a quantity which is functionally differentiable. By the way, this is also true for the total Hamiltonian of the theory. It has to be functionally differentiable, and you have to be careful with boundary terms. Now, the second thing which we will use, and this is important in the covariant phase space formalism, is that once we have these quantities at hand, we can easily compute the Poisson bracket. So now basically what we're saying is that instead of computing the Poisson bracket in the in the usual familiar Dirac Hamiltonian picture, of course here we didn't do any Dirac Hamiltonian analysis or anything like this, but still we can compute the Poisson bracket between two generators, one for a parameter epsilon 1 and the other one for parameter epsilon 2. Well, this we can do because if we go back a few slides before, of course, if you allow me to go back, if it's not, okay, yes. Again, we have to remember that the symplectic structure is a two form in field space. So in the beginning, it had two variations. Once we contracted the symplectic structure with a variation, we're still left with a one form in field space. So there is still a field space entry with a variation delta. So now if we take both entries to be a variation, see, we evaluate the symplectic structure omega on delta epsilon 1, delta epsilon 2. By construction, this is just computing the action of the transformation delta epsilon 1 on the generator h of epsilon 2. So by construction, by definition, this is the Poisson bracket between h1 and h2. Now we can announce a result which we won't prove it here, but the proof is in many beautiful references, and I will give them to you at the end of this chapter. And I invite you to check this proof. So this proof kind of mirrors or reflects what we had, I think, on the first slide. On the first slide, we said that for a simple mechanical system, the set of Noether charges forms a Lie algebra. Well, here, kind of the generalization of this statement is that under this Poisson bracket now, which we can evaluate by contracting the symplectic structure twice with two variations, if the charges are integrable, and this is an important point, but if the charges are integrable, so if they really exist, if these generators exist on phase space, well, then the Poisson bracket reflects the symmetry algebra, so the algebra between the parameters epsilon 1 and epsilon 2, up to a term k, which we call a central term. So this term, which is a central term, I just list one of its properties here. Essentially, the property that this term is central, we will again give examples of this. So the first one is that this is a quantity which does not depend on the fields, and it satisfies this so-called two co-cycle condition. So this is a cyclic identity. So we will see examples of these terms popping up, appearing when we compute algebras of generators. And also I realize when I say this that I'm apologize because I'm already making kind of taking a shortcut, because I'm now referring implicitly to the generators as charges. You see the bold sentence, I talk about integrable charges, but I refer to H, because now I hope this is okay now. So again, we're always on shell in this covariant phase space formalism. And because of this, we want to think of these generators as being, so the physical information which survives when you are on shell is precisely the boundary term, is precisely the charge. The only thing, again, which we have to keep in mind is that if we just say charge, it's not actually the Noether charge, because again, if we go back to this slide here, on the boundary, we don't only have Q, not only the Noether piece, but there is possibly another piece coming from this F term. So, okay, if you allow me this simplification, I just refer to this whole thing as the charge of the transformation. So now we want to apply this to general relativity to be a bit more hands-on and see concretely how this works. So to apply this to general relativity, well, we have to gather a few ingredients. The first ingredient is to, of course, recall that the gauge transformations now, they are diffeomorphisms, space-time diffeomorphisms. And the parameter, which previously we called epsilon, is now a vector field psi. So what we mean by delta of psi is a Lie derivative, which I'm writing now in differential forms using this so-called Cartan magic formula. So this is the formula for Lie derivative acting when written in terms of differential forms. And now the other property we need is that when we compute this Lie derivative of the Lagrangian, well, you can see that you get a boundary term. And this boundary term is just a vector field psi contracted with the Lagrangian seen as a D form in space-time. So now if we go back on what we had a few slides ago, for the Hamiltonian generator, we found this expression. So see here, I'm just going one line before the equality we had earlier. If you remember earlier, I used this, this kind of simplifying assumption to put the bulk term here, delta B minus delta epsilon theta. I wanted to show that this goes on the boundary. And I used the simplification, I used the little assumption there. I want to just show what happens in the case of general relativity. So I just go one line before. This is what we found for the Hamiltonian generator. Now we can explicitly evaluate the bulk piece. Because for general relativity, so we just showed that this bulk piece now, so delta B minus the Lie derivative of the potential theta. So delta B now, I take the variation of the boundary term B, and I get the vector field psi contracted with delta L. Again, just notice that the fact that I'm letting the variation delta go through the vector field psi. So I'm kind of implicitly assuming that the vector field psi does not depend on the fields. And now the Lie derivative acting on theta, well, it's just the Lie derivative acting on theta. Now in red, you see we use again the variational formula for the Lagrangian. So we get the equations of motion, we get D of theta again. And in orange, I just use Cartan's magic formula for the Lie derivative. And you see that the two terms in the middle, they cancel each other. And we're left with a piece which is proportional to the equations of motion and a boundary term. So if you put this together, the first equality and the three equalities which come later, we finally get our result, which I put in a box now, which is that in the case of general relativity, when you go on shell, you indeed get that the Hamiltonian generator of the diffeomorphism with vector field psi is equal to a boundary integral. This boundary integral is the integral of the variation of the neutral charge Q minus this non-integrable type of piece, which I called F earlier. But now we have a more precise characterization of this piece F in the case of general relativity. And in the case of general relativity, this piece is the vector field psi contracted with the symplectic potential. And again, because the symplectic potential is a one form in field space, there is a delta, a variation which sits somewhere in the symplectic potential. I'm not allowed to pull this variation out of the expression and to get a purely variational quantity here. So to be more precise, we don't know how to make this charge integrable for the moment. Again, this is the reason why we use this notation delta slash, because this quantity is not yet integrable. So by the way, I encourage you to check this, this beautiful paper by Wald. He has a paper called Black hole entropy is neutral charge. And essentially, the starting point for this proof that black hole entropy is neutral charge is this formula which is in the box here. So hopefully now you understand where this formula comes from and you can easily read this paper. So now the other thing I want to mention is that, as we said, this quantity is not yet integrable, and precisely the obstruction to integrability comes from this piece, which I call, usually people call this a flux piece. You see, if this quantity was integrable, well, it would mean that delta slash of H is actually a total variation delta. So if I take a second variation, because delta squares to 0, I should get 0. So I can measure the obstruction to integrability by taking delta of delta slash. So the neuter piece drops because we have delta square of Q, and we're left with psi contracted with delta theta. Delta theta is just a symplectic current. And you see that this obstruction to integrability is intimately related to what we discussed, I think, a few slides ago when we introduced this covariant phase space formalism, is that the obstruction to integrability is actually intimately related to the question of the conservation of these charges, the question of whether there are degrees of freedom leaking out of our system, or whether the system is actually closed. And we will be a bit more explicit and come back to this very important point. But at least now we have this, this important formula. Now we want to be even more explicit in the case of general relativity and list all these things. So the first thing is, okay, what is actually the diffeomorphism Noether charge Q in general relativity? The second thing is, what is the meaning of Noether's identity? We said that when you have a gauge theory, there is this Noether second theorem, which gives us an identity. What is the geometrical meaning of this identity in the case of general relativity? And lastly, what is the explicit expression for the Hamiltonian charge? Because again, now we should understand this distinction between two concepts. One of them is the Noether charge, which has an analog in mechanics, for example. But the other one now is the Hamiltonian charge. And you see in this box here, again, that the Hamiltonian charge and the Noether charge, they don't necessarily agree. So what is the full explicit expression for the Hamiltonian charge? This is what we want. And once we have it, we will use it to see some cool stuff. So applications to general relativity. So how do we use this? So there is already here a footnote flashing because, so we start of course with the simple setup. So the Einstein-Hilbert Lagrangian. I debated whether I should write this really with forms or with, or how to do this. So I chose here to write this in differential forms. So you can think of this L as a top form, as a d-dimensional form. And to do this, I have put this, this volume factor in front, which is a 4 form. So this V you see in the footnote has D for X, the 4 form, the volume element square root G. And this is such that we have this nice compact integration by parts formulas. So this is just a notation that we use here, but you're free. I invite you to translate this into any form, any notation, any language you want. So now we can repeat kind of the steps that we had very formal steps earlier. Now we have a precise theory, we have a precise setup. We can repeat these steps and see a bit, see what happens. So first we compute the variation of this Einstein-Hilbert Lagrangian with cosmological term. And of course we get the expected result that the variation, I isolate here the equations of motion, G mu nu plus lambda small g mu nu. So capital G mu nu is the Einstein tensor, and times the variation of the metric with upstairs indices. And to do this, we have to, of course, once again, integrate by parts to isolate the equations of motion. This produces a boundary term. And this identifies for us the symplectic potential. And so if you just repeat this step of computing the variation of the Einstein-Hilbert Lagrangian, you will easily convince yourself, easily see that essentially this symplectic potential comes from the G mu nu delta R mu nu term of the variation of the Lagrangian. So the Ricci scalar is a G mu nu R mu nu. And then when you vary the Ricci scalar, you have to vary G and vary R. And it's the contribution from the variation of the Ricci tensor, which essentially gives you it's a boundary term, which gives you the symplectic potential. And I have given here two expressions for the symplectic potential. One is in terms of the Christoffel coefficients, and one is also in this more explicit form with the metric. You see, so it's kind of a funny property of general relativity that the symplectic potential itself is a derivative. It's a nabla nu of this expression on the right. This is just a peculiarity. It's just, you will see it's not generically the case, of course. Now we can ask about Noether's second theorem and ask what this identity is. So we can just apply, I mean, we just want to check that Noether's second theorem is indeed true, and of course it's true, but we want to see what it tells us here in general relativity. So if you remember, Noether's second theorem was a statement about, so again, we have this variational formula telling us that, so by the way, some authors, I think Blau in his lecture notes, he calls this the master variational formula, because it's a very useful variational formula from which you can easily, as we did, derive Noether's theorems and conserved quantities and things like this. So this master variational formula tells us that the variation of the Lagrangian is the equations of motion times delta of the fields plus d of the symplectic potential. So now we take the equations of motion times delta g mu nu, and we just take now delta g mu nu to be a gauge transformation. So delta psi of g mu nu. And we ask what becomes of this piece. So Noether's second theorem tells us that this piece should be a boundary term of shell, should be identically a boundary term. So to show this, we just replace the variation of g by the Lie derivative. I get -2 because I'm varying g with upstairs indices. So I get -2 nabla mu of psi nu. And now you see if we just integrate by parts this nabla, I get up to a boundary term, essentially the Bnk identity. So I get nabla nu of g mu nu, the Einstein tensor, but this identically vanishes by virtue of the Bnk identities. So this is the illustration in the case of general relativity of this fact, this powerful fact, which is encoded in Noether's second theorem, which is that when we have gauge symmetries, there are identities satisfied by some geometrical objects in the theory. And here the expression of this in general relativity is the Bnk identity. So as expected, the theorem holds, and we get that this term is strictly equal to a boundary term. Now we can apply the formula for, so we started with the second theorem. Now we go to the first theorem. We do it in reverse order, and we can compute the Noether current. We can compute it on shell because we just want to access this piece Q, the Noether charge. So to do this is just an explicit detailed calculation. So we just go back to the definition of what we call the Noether current. So this is the symplectic potential evaluated on the variation, the gauge variation, so delta psi, minus the boundary term produced by the variation of the Lagrangian. In this case, it's psi contracted with L. So we compute this explicitly. So it's just these 3 lines. So we just have to do some integration by parts and rearranging these terms a bit. And no, sorry, there is in fact no integration by parts used here. It's just a rearranging of these terms. And if you do this, essentially you massage this term in such a way that the equations of motion appear on the boundary. Then you can go on shell, in the last equality, and you get the expression of Noether's first theorem. So in more compact notation, we have shown that on shell, the Noether current is indeed d of something. So if I reintroduce indices with this form notation, this something is a codimension 2 quantity, q mu nu. And this is what in general relativity is known as the Komar charge. So this Komar charge is what plays the role of the Noether charge for diffeomorphism symmetry in the case of general relativity. But now, as we just showed before, when you ask the question, what is the Hamiltonian charge associated with a transformation, like a diffeomorphism, we just showed that the answer is not only the Noether charge, so not only the Komar charge Q. There is also the other piece. And now the other piece is given here. So this is the expression for the full charge. The full charge on shell is given by this expression. So I'm not giving a proof of this, but because it's a bit, it's not very visual, in fact. But if you want to compute this, you just have to, sorry, if I go back a bit, you can actually explicitly compute this quantity in the box here in the case of general relativity, because now you know what the symplectic potential is, we know all the quantities, and if you compute this, you will show that the full charge has this variational expression. So again, I'm writing explicitly the on-shell equalities here. So we are left with a surface integral, and it's the integral. There is a codimension to volume factor, v mu nu, and then a codimension to object, which is the charge. And what is important to notice is that the variation is inside of this quantity. So a few comments now. The first comment is that what I said before is that for some of the calculations, because I didn't want to take shortcuts or to miss something, but I just wanted to stress the fact that explicitly we assumed so far that the vector field psi was field independent. But actually this variational expression, which I give here, so this full expression for the charge, is also valid even if the vector field psi depends on the fields. And you can actually show this. It's a bit more work to keep track of everything. And I think we will come back to this in the very last section, because this is more, so the chapter which I call advanced topics. But for the moment, you can just take at face value this, take this for granted, this result, that this is the full charge, and that this is the general expression for the charge. There is no assumption here. There is nothing that we lost. So yes, our goal will be to understand precisely now the subtleties associated with these charges, kind of compute them in some explicit examples. And
you have 5 minutes left, Marc.
Yes, okay, yeah. So you will see what I will try to illustrate is that, well, in fact, I don't know if we will show this, but what you should keep in mind is that, in fact, these charges may not be finite. It actually depends on how and where you define them. Well, these charges may not be integrable in general. As we said, you're not guaranteed that this quantity exists as a total variation. And by the way, I think I also briefly mentioned this. If the charge is not integrable, then the representation theorem fails. Then you don't know a priori. A priori, it's even hard to make sense of the meaning of the Poisson bracket between charges which are not integrable. You may have to use a bit more assumptions and things you put in by hand to define this. And we will also go back to this in when we study more advanced things. Well, what can also happen is that, of course, this charge may also not even be conserved in time. And this is the case, as we will derive, of the famous Bondi mass loss formula due to gravitational radiation. So if you evaluate this for a general enough spacetime, which admits radiation, then you can show that this charge, which is, in some case, you can try to define the energy of your spacetime. And so this Bondi mass, which is measuring the energy, you can show that this is not integrable, but it's a decreasing function of time because the system is losing gravitational energy due to radiation. So what we want to do is now, so before going to these more advanced things, to understand a bit more precisely how to use this formalism, these charges in general relativity, I first wanted to make a detour through three-dimensional gravity. So the reason is that there are many reasons. In fact, the first one is a bit silly, is that 3 is between 2 and 4. Okay, that's silly, but it's just saying that, in fact, it's also interesting to study this in 3D gravity. It's a kind of rich, and probably you know that there's a lot of recent work dealing with two-dimensional gravity. Two-dimensional gravity is actually very rich, and many of the structures which we're discussing here is useful in two-dimensional gravity, but it's a bit, in a sense, it's more complicated than three-dimensional gravity. So that's why I didn't want to discuss it, but 3D gravity is easy enough. Also, the reason is that it's actually there. So in three-dimensional gravity, that holography, or what we in the most simple expression is ADS3 CFT2. This is where this was discovered. So I want to briefly explain how this was discovered and what is the expression of this in terms of these gravitational charges and gravitational symmetry algebras. And also the last reason is that after all, this is a course, I mean, this is a summer school on quantum gravity, and there's lots of also ingredients of loop quantum gravity. And a lot is known about three-dimensional quantum gravity, and also more precisely, three-dimensional loop quantum gravity. And because of this, I thought it was a kind of a nice occasion to, while we discuss these charges and symmetries in general relativity, to also discuss the case of 3D gravity, because it gives you kind of tools and it tells you some stuff about, useful stuff about 3D gravity, which you can use when quantizing three-dimensional gravity. And now maybe I stop with a biography for this section. So yeah, these are maybe by order of complexity here. You can maybe start with the first one. The second one is maybe, I will come back to this again in the advanced topics, because it discusses some subtleties of the covariant phase space. And a very complete and beautiful reference is the last one by Compere and Fiorucci. And basically the first half of this, or the first third of these lectures by Compere and Fiorucci is what we covered a bit in very condensed way today. Yeah, so hopefully today we can do, tomorrow we can do 3D gravity and 4D gravity. And next Monday we will see, either we do only advanced topics or also some numerics. And maybe we can take some questions now. I think we...
Yeah, thank you very much, Marc. So now if you have any question, just raise your hand and we will unmute you. Or if you don't want to talk, you can just write the question in the chat. And it was so clear, there is no question.
In the chat. Someone has a raised hand. Is it?
Oh, yeah.
Hi, do you hear me?
Yes.
Yes.
I have a question on some of the last slides. You have this volume V, then you define V mu and V mu nu, and I don't really understand what they are. It was, I mean, if you can say a word about this term.
This is just, yes. So the definition of V mu was given here in this footnote. But if you want, you can more easily understand this if I retranslate this in space-time form, I mean space-time language. You see, if you were to take this object theta, so see in the boundary term here, I wrote, so the first equality, I wrote V mu of theta with upstairs indices. Now, if you were to actually integrate this on a space-time manifold, so theta is a d-1 form. So you would integrate this on a d-1 dimensional manifold. But on this manifold, you would need the measure, the volume element, and also the normal. And the normal is what comes contracted with V mu, or sorry, with theta mu. So to actually write this as an integral, you would integrate over square root of g times n mu, the normal to the surface you're integrating, and this normal n is contracted with theta mu. And the same is here with these codimension 2 integrals. V mu nu just stands here for what is called the binormal, because S now is a codimension 2 surface. So it has 2 normals. Let's call them S and N. And V mu nu is just the binormal to this surface. So V mu nu here is the volume element on the surface times the binormal, which is the anti-symmetrized normal NS minus SN. I don't know if this was clear enough. So yeah, you can think of this as being the volume element and the normal, if you want.
Okay, thanks.
Any other question? There was a question in the chat, Marc.
Would you recall what was the representation theorem you said fails when the Hamiltonian charge is not conserved in time? Well, so yes, so the representation theorem I refer to is a theorem that tells you that when the charge is integrable, the Poisson bracket of the charges is reflecting the so in this case, for example, for general relativity, the parameters are vector fields. So the algebra of the charges is the same as the charge evaluated on the algebra of the vector fields up to a central extension. So the Poisson algebra of the charges has to reflect the algebra of the vector fields or the algebra of the gauge parameters that you have in your theory up to central extensions. And in the case where the charges are not integrable, this theorem fails. So you don't know a priori what the Poisson bracket is. And in particular, what you can have is that if you naively compute the Poisson bracket by contracting twice the symplectic structure, if the charge is not integrable, you will, for example, produce central terms, but which are not manifestly central because they are actually field dependent. Someone asked about the Komar charge. Does the killing field need to be time-like? No, the killing field, the way we define the Komar charge, the killing field does not need to be, to any killing vector, you can associate one such Komar charge. Then the physical question is whether there are situations, spacetimes, so two things go hand in hand, the spacetimes and then the symmetries that the spacetime may admit. And what you want to ask is if there is a setup, the spacetime in which you're interested, in which you can, for example, compute the charge evaluated for example, a time translation vector field, and whether this gives you, for example, the energy of the system. But again, for this, you would not just compute the Komar charge, you would compute the full Hamiltonian charge. And we will do examples of this, computing the angular momentum and the mass of a black hole, for example, using these charges.
Someone raised his hand before a Farid question. So Sami Violet, I'm unmuting you.
Hello, do you hear me?
Yes.
Okay, so just after the break, you explained that sometimes it's the bulk part, so the constraint, which is the generator of the gauge transformation. But before that, you said that it was a full H which generates the gauge transformation. So I didn't really understand
yes.
what is at the end. What is the generator of the gauge transformation?
Yes, sorry, this was my my mistake because probably I used the same sentence for two different things. What I said is, if you want, if I rephrase, if we didn't know about the covariant phase space formalism, if we just knew Dirac Hamiltonian analysis, usually we do Dirac Hamiltonian analysis without, let's say you do it on a manifold without boundaries. So sigma has no boundary. Then what Dirac gives you, the constraint, is indeed the generator of your gauge transformation. Now, if your manifold has a boundary, this is where you have to be careful. This is not true anymore, because as we said, since the constraint has a derivative, it has to be functionally differentiable. And when you compute its variation, it produces a boundary term. So if you have a boundary, it's not true anymore that the constraint in Dirac's language is the generator of the gauge transformation. But what gives you the true generator of the gauge transformation is what we constructed to be H. So this is why I distinguished H from C. C, which is constructed from the off-shell piece of the Noether charge, is Dirac's constraint. This is not generically the generator of the gauge transformation. But H is the generator of the gauge transformation. Is this okay?
Yes, okay, thank you.
So in fact, the safe definition to take is always H. You can use this covariant phase space formalism, define H, and you're always guaranteed that H is the good generator. Because if you don't have a boundary, then H and C will agree because they only differ by a boundary term. So if there is no boundary, they will trivially agree. And if there is a boundary, well, H will precisely contain the exact boundary term to turn C into a differentiable object. So C itself is not differentiable, but C plus the good boundary term is differentiable. And C plus this good boundary term is precisely H.
Okay, great. Thank you.
So there is someone asking if the symplectic potential is gauge invariant.
It's not. No, it's not. For example, you can see. So this question I think can mean two things, but for the two things which it can mean, it's not gauge invariant. So the first thing it can mean is like on this slide. On this slide, we have a quantity which is delta epsilon of theta. So if by this you mean you take theta and you compute each gauge transformation, then you see on this example of diffeomorphisms that it's not gauge invariant, because you compute the Lie derivative, you act on this with the Lie derivative, and you get you get this orange expression. You don't get zero. So in this sense, it's not annihilated by the Lie derivative. It's also not gauge invariant in the sense, the other sense you could mean that if you take theta as a one form in field space and replace the variation inside by a gauge transformation, generically this will also not give you zero. So theta is generically not a gauge invariant object.
Pierre is asking, what is your physical intuition about the second and third theorem?
My physical intuition. Yeah, I'm not sure what.
Pierre, can you talk to make maybe your question more precise?
In fact, I think I cannot say more than what I don't understand. You know, I think this question is related to the more deep question, which is why we are dealing at all with gauge theories, you know, and these redundancies and these constraints and these undetermined parameters and these identities between. And I don't know what the deep reason for this is. But.
Yeah, the motivation for the question is because for the first theorem, I think the physical intuition is quite clear. Like we have conserved quantities, we have symmetries, and there is a correspondence between the two. Mm-hmm. It's kind of intuitively we understand what is a symmetry, mm-hmm. and we also have a clear understanding of what is something which is conserved, such like the energy.
Ah, okay.
So that's for the first. We have a clear, I think, almost experimental understanding of what this means. The first theorem. So I was wondering if you had such an understanding for the second one.
I think then I would say it's because it's precisely telling us that you know, you have certain objects which satisfy actually identities which don't have independent components because you have gauge symmetries. So I think it tells us that there is some amount of redundancy in the quantities that you are working with in your theory. But then I don't want to say that, I know this is a bit a debate, you know, I don't want to say that gauge is pure redundancy and that, that's what I don't want to say, but.
There is one last question in the chat asking what is the central extension of charges in general relativity?
Well, that's the crucial question we have to study and answer. In fact, there is no canonical answer because the central charges depend on actually which theory of general relativity you're describing, and if it's in 3 dimension or in 4 dimension, and which space-time you're describing, and which vector fields you're looking at and which spacetimes. But this is what we want to give examples of this and see what the meaning is. So in the next chapter for 3D gravity, we will give examples of these central extensions in general relativity and try to explain what they mean, what is their physical meaning. But there is no general result that tells you this is the central extension.
Okay. No more questions? Well, then we can thanks Marc again, and I think we will start in half an hour.
Thanks everyone, and we'll see you tomorrow, I guess.
And in half an hour for Maite.
Yes, yes.
Course. And for the coffee break, there is the Gather Town room that you can go if you want to discuss with people or work on a blackboard with others.
Right.